All right, let's talk about a couple of different forces in more depth. The first one being weight. Now, when we talk about weight, what we're talking about is a measurement of the gravitational force acting on a mass. Now, think back to the equation we just saw in Newton's second law, where force is equal to a mass times acceleration. Well, in this case, this very particular force, the force of gravity, right, is equal to your mass times an acceleration. And in this case, it's a very particular acceleration, the acceleration due to gravity, right? So if you want to find the weight, the amount of gravitational force acting on any object, you just need its mass and the gravitational acceleration of wherever its location is. Now, you want to be very careful when you're talking about weight and mass in especially these conceptual questions, because there's a huge difference between weight and mass, right? Mass is how much matter something is made out of, whereas weight is the amount of gravitational force acting on that mass, right? Your weight can change based off of your location, whereas your mass is not going to change, right? So there's a big difference there. So you want to use your language very, very carefully. For instance, let's say, you know, here you are, here's the Earth, and you're standing here, right? Like let's say you've got a mass of 80 kilograms. Well, you've got a weight that is 80 times 9.8 here. But if I somehow magically teleport you to the moon, is your weight the same? No. Your mass is still 80 kilograms, right? Because you didn't lose an arm in the teleportation process. But your weight is significantly less. It's 1/6 of your weight on Earth, right? So your weight changes based off of location, but your mass remains the same. So again, weight is a measurement of the gravitational force, whereas mass is a measurement of how much stuff you're made out of. So if we look at the example problem in the notes here, we've got if a cube has a mass of 90.91 kilograms and a weight of 890.9 newtons on Earth, what will its mass and weight be on the moon, where g is equal to 1.62 meters per second squared? All right, so on Earth, cube has a mass of 90.91 kilograms and a weight, so again, Fg, that's your weight, force of gravity, is 890.9. And we want to know its mass and weight on the moon. Well, this cube is going to have a mass that doesn't change based off of location, right? Its amount of matter is identical whether it's on the Earth or the moon. But its weight on the moon is going to depend on the moon's gravitational acceleration. So if we look at Fg being equal to mg, your weight is equal to the mass of 90.91 kilograms times the gravitational acceleration of 1.62 meters per second squared. So you get a weight of, let's see, 90.91 times 1.62, 147.3 newtons. Right, so while mass didn't change based off of location, the weight, the force of gravity acting on that mass, varied greatly. Right, so again, that's the key thing to understand is the difference between weight and mass. Right, that's something you want to pound into your head. Now, one other thing we want to talk about with regards to weight, and this comes up a lot in questions dealing with elevators, especially conceptually, is this idea of how heavy you feel. Right, so this apparent weight is what we call it, or perceived weight, is how heavy you actually feel. And that can vary based off of your acceleration. Now, it is not a measurement of gravity, right? You weigh the same whether you're accelerating upwards or downwards, but you're going to feel heavier or lighter depending if you're accelerating upwards or downwards. What it's tied to is the normal force. So, how heavy you feel is dependent entirely on how hard the surface is pushing on you. Um, Take, for instance, this is getting a little ahead of ourselves, but we'll cover this in detail when we get to circular motion. Take, for instance, that carnival ride, right? Where you walk into that room and you stand up against the wall and the room starts spinning. Well, what do you feel when that room starts spinning and the floor drops down? You're stuck to the wall, right? You feel super heavy. Are you actually heavier? Do you actually weigh more? No, the force of gravity is still your mass times 9.8 meters per second squared. So your weight doesn't change. But why do you feel heavier? Well, it's because that force, normal, right? The surface pushing back on you increases the faster that thing spins. Now, if we're talking about elevators, it's all going to depend on your direction of travel and the acceleration. So let's say you're in an elevator and you are, well, it doesn't matter what direction in this case. Let's say you're traveling up or down, doesn't matter. But you're traveling at a constant velocity, meaning that your acceleration is 0 meters per second squared. So this elevator is, say, between floors, traveling at a constant speed. Now, if you're traveling at a constant speed, right, at a constant velocity, and your acceleration is 0 meters per second squared, that means that your net force is 0, right, which means that you're in a state of equilibrium. So if you're in a state of equilibrium, the normal force and the gravitational force are going to be identical. So if the normal force and the gravitational force are identical, you feel your true weight. Right? So you feel as heavy as you actually are. Now, as we go through these elevator scenarios, keep in mind that if your normal force is greater than your actual weight, you feel heavier. If your normal force is less than your true weight, you feel lighter. If the normal force is equal to your true weight, well, you feel your true weight. Now, if the normal force is 0, that's when you feel weightless. Right? Are you truly weightless? No. You still have a force of gravity acting on you. You just feel like you're weightless because the floor is not pushing on you. So again, the apparent weight is all tied to the relationship between how hard the surface is pushing on you and your actual weight, the force of gravity. So let's say that you are in an elevator and you're going up. And there's a downward acceleration. So this scenario would be you're going up and you're approaching the top floor, so the elevator is slowing down. Well, in that case, you have a downward acceleration, which means you also have a downward net force, which means that the downward vector, your weight, is larger than your upward vector, the floor pushing on you, the force normal. So in this case, you're going to feel lighter than you actually are. Now, let's say you're in an elevator again, and you're going up, and the acceleration vector is upwards. So basically, this would be, say, you're leaving the bottom floor. The elevator's starting to move up and it's building up speed. Well, if the acceleration is directed upwards, your net force is also directed upwards. So if your net force is directed upwards, you know your upwards force is greater than your downwards force. Well, in this case, the floor is pushing on you with a greater force than your actual weight is pulling down on you, so you feel heavier. So it's all about looking at the direction of the acceleration and then analyzing the normal force versus the gravitational force, right? Whichever way the acceleration points, that's also the direction that your net force points. So if your net force is upwards, you know normal force is greater than gravitational force. If your net force is downwards, you know gravitational force is greater than normal force. And if your net force is zero, well, you know that you're in equilibrium, right? Both forces are identical. And so again, your apparent weight, your perceived weight, how heavy you feel is all going to be tied to this relationship between the normal force and your actual weight, the force of gravity pulling on you. Now, one thing to keep in mind, if you've got these conceptual questions that deal with someone standing on a scale in an elevator, a scale doesn't measure the force of gravity. A scale actually measures the normal force acting on an object. So in this case, if you were standing on a scale, it would read your true weight. In this case, if you were standing on a scale, it would show that you were lighter than you actually are. And in this case, if you were standing on a scale, it would show you heavier. Because a scale, again, is a reading of the normal force acting on you. So let's take a look at that example problem at the end of the weight section. So we're told a friend has given you a special gift, a box of mass 10 kilograms with a mystery surprise inside. It's a reward for your fine showing on the physics final. The box is resting on a smooth, frictionless, horizontal surface of a table. So determine the weight of the box and the normal force acting on it. So part A, you always want to start with the free body diagram. We've got our box. It has a mass of 10 kilograms. There's a normal force, and there is a gravitational force. Right, the weight. Now you're going to notice a lot of times I'm not even going to write FG, I'm just going to write MG. That's perfectly fine to do if you want to do it as well. Alright, so we want to find the weight of the box and the normal force acting against it. Well, first off, this box is just sitting on the table right now, right? So if it's at rest, we know its acceleration is 0. We know its net force is 0. So we know that's in equilibrium, meaning that these two vectors need to be identical, right? Because if you look at net force being equal to 0, you'd have Fn minus force of gravity equal to 0. So your Fn has to be identical to your weight. So let's find our weight. So Fg equals mass times gravitational acceleration. So force of gravity is equal to 10 kilograms times 9.8 meters per second squared. So the force of gravity acting on that box is 98 newtons. Right, and because you're in equilibrium, your normal force also equals 98 newtons. Alright, in the next scenario, your friend pushes down on the box with a force of 40 newtons. And we want to determine the normal force acting on the box. So again, let's start with the free body diagram. Mass is still 10 kilograms. You still have mg. And this time you also have an applied force of 40 newtons downwards. Now this box is not crushing through the table, right? Which means that the normal force has to be pushing up with enough force to not only counter the weight of the box, but also the force that your friend applies, right? Because again, if the table is not breaking, the table is pushing up with the same amount of force as the weight of the box and your friend's downward force. So we know the weight already is 98 newtons, right, from earlier. So if we look at our net force equation, net force equals 0, because again, the box is still at rest. It's still in equilibrium. So if our net force equals 0, your normal force minus the weight minus that applied force has to equal 0. So your normal force has got to equal the sum of your downward forces. So your normal force equals 98 newtons plus those 40 newtons. All right, which is 138. Right, so the table's having to push upwards harder, right, to counteract that additional downward force. Now in scenario C, we got your friend. He pulls upward on the box at the force of 40 newtons. And now we want to know what is the normal force on the box. All right, again, start with the free body, 10 kilograms. We still have that force of gravity down here, right, which is still 98 newtons. Now in this case, you've got an applied upwards force of 40 newtons. And we've got a normal force. Now in this case, your friend is supporting some of the weight of the box, which means that the table doesn't have to push up so hard, right? Because of this extra upward force that is supporting this weight. Your acceleration is still 0. You're still in equilibrium, right? So we still know that net force is equal to 0. Now in this case, we've got two upward net forces, your Fn and your applied force, minus your weight is equal to 0. So rearrange, you get your normal force is going to be your gravitational force minus that applied force. So your normal force is 98 newtons minus 40. So the normal force exerted by the table on the box is 58 newtons. Yeah, because again, the table doesn't have to support as much of the weight anymore because your friend is pulling up on the box. So again, remember, there is that big difference between mass and weight. And also, there's a big difference between how heavy you feel and how heavy you actually are. So those are a few ideas you need to get straight in your head, right? The difference between mass, weight, and perceived or apparent weight. Now, tomorrow I'll be uploading a video on the second force that we want to focus on, and that would be friction. Yeah, see you in the live engagements.